tricks we can talk about using to solve this problem. The first one is a quite general trick, and it'll work for any of the problems you see in this class, and really it's general enough to tackle a very wide range of constraint maximization problems that you'll encounter in economics at least. And so that very general approach is to use the method of Kuhn-Tucker. And I'm going to refer you to the notes I handed out at the beginning of the semester on all the math you need to know to be an economist, which has a pretty careful description of that method and also a recipe for solving these problems. A second thing you can do, which is a little bit more special but related, is to formulate this thing as Lagrangian. Now, so the method of Kuhn-Tucker, you may already know this, I'll say it anyway. The method of Kuhn-Tucker allows you to solve maximization problems that have inequality constraints. So this problem is an example of that. We've got an objective function, we've got an inequality constraint, and so Kuhn-Tucker is the usual way to solve problems like that. The method of Lagrange is another way to solve constrained maximization problems, but it only works if you have equality constraints. So it doesn't actually apply to this problem unless you're prepared to assume that the budget constraint is satisfied with equality. And now it so happens that in this case, because there's non-satiation, it's never optimal for the consumer to leave some money left, to not spend all their money. Remember, the problem, the consumer only cares about consumption today. She dies at the end of the day or something. So she should spend all her money. And so it's a characteristic of this problem that even though we have an inequality for a constraint, at the solution, it's always going to be satisfied with equality. Now, if you already know that or can prove it or are willing to assume it, what you can do is say, okay, I'm going to rewrite this thing. I'm just going to assume, or I can prove that this thing is satisfied with equality. And once you've done that, you have a couple other options for solving this problem. The first one is the method of Lagrange, which I already mentioned. So that allows you to write down a Lagrangian and solve that thing using the tools of calculus. Works great for problems with equality constraints. Okay, so that's method 2. So if you're willing to assume the constraint is binding, you can go ahead and solve it that way. You can go back and check after you're done to make sure that you weren't wrong about the solution, about the constraint being binding to the solution. So that's another way to proceed. Then there's a third way to do this, which doesn't involve as much scary math, although it's actually a little bit more work for some problems. The third approach is to, again, assume that the budget constraint is satisfied with equality, so the person spends all their money. And then what we'll do is we'll use that extra equation we get, since it's an equality, we can use that equation, and use that to eliminate both the constraint and one of the choice variables in the problem. And then we can actually turn this thing into an unconstrained maximization problem and solve it again using the usual tools of calculus. Okay. So any of these things, in fact, any of these tricks really these are all different tricks for turning a constrained maximization problem into an unconstrained maximization problem. And once we've done that, we can go take first order conditions and solve them and go to town. Okay. All right, so that's the overview of ways to tackle this thing. I'm going to go through one of these methods, but maybe I should stop and see if there are questions first. Okay. All right, so let's go through a detailed example of this. So I'm going to use the third method here, in fact. So what I'm going to do is start by assuming that the budget constraint is satisfied with equality, and then just rearrange it. So I don't know if you recognize it here, but once the budget set holds with equality, I can just rearrange it this way and write this thing. So I know, and let me talk through it a little bit. What I've done here is I said that x1 has to be equal to your total income minus your total expenditures on the other good divided by the price of the first good. That's all this says. Okay, and so if the budget constraint is satisfied with equality, this has to hold. Okay, so now I've got an expression for x1 that's just in terms of prices, income, and the good x2. And so I can use that. I'm going to do that by using this thing and substituting this. This is really just another way of writing the constraint. I'm going to substitute this into the objective function so that I wind up with this expression. So remember, I had the objective function previously. The unconstrained problem looked like this. I'm assuming this holds with equality. I'm using this equation to eliminate x1, eliminate both the constraint and the variable x1 in this objective function. Okay, so, and there we are. So now notice two things about this. First of all, there's no constraint. I put it in the objective function. Second of all, there's only one choice variable now. Y and the prices that we all think is given. Those are just numbers as far as the consumer is concerned. The only thing the consumer has to do now is to choose x2. And her choice of how much x2 to consume, leaves some money left over in the budget, and then she spends all that money on x1. Okay, so that's one way to think about a now unconstrained version of the maximization problem facing the consumer. A problem with no constraints and only one choice variable. Okay, is everyone happy with that? Yes.
I have a question about the first part. How do you show in your work that you're assuming that it's constrained?
I would just
say that you assume it.
Like in a problem, if I write this down, I would say assume that the budget constraint holds with satisfied with equality, or else you can there are different ways you can prove it, or you can go back and verify it. You can get a solution given the assumption, then go back and make sure that that in fact things work at the solution. Okay, yeah. Okay, so with an unconstrained maximization problem like this, what do you suppose the next step is to solving the consumer's problem? I like this answer. So now we're going to start using calculus. We're going to get the first order condition for this problem by taking the derivative of the objective function here with respect to the choice variable x2. And does anyone remember what's the logic behind? Why will that tell me something about the solution? So that when we're thinking about actually maybe we can see this here. Think about this thing as a function of x2. If you're going to graph this function, then we've got a piece involving a log, which is strictly increasing. We're adding that to a piece involving x2, which is linear and strictly decreasing. And so we've got a function here that goes up for low values of x2 and then eventually goes down. And at the top of that hill, it's smooth. At the very top of that hill, the slope is equal to 0. So we're going to use the calculus here to find the point on that curve where the slope is equal to 0, and that's going to tell us that we're at the top of the hill. That's the idea. Okay, so I'm going to do another trick here first to make the calculus a little simpler even. I'm going to simplify this thing just by using these log tricks. So I'm going to wind up with alpha times log y minus b2x2. So notice, by the way, what's y minus b2x2? Yeah, it's expenditures on good 1. Okay, and then we've got this piece involving p1. This isn't going to show up in our first order conditions because p1 isn't a choice variable. And we've got this piece with log x2. Okay, so we've got this unconstrained problem. We're going to take the partial derivative of the objective function here with respect to x2. That's this. We set it equal to 0 because we want the point at the top of this objective function where the slope is equal to 0. And now we've got an equation, not too complicated at all really, that involves just a single variable. And so we're now back in the realm of high school algebra where we can just solve this thing for x2. Okay, so if we do that, I'm going too fast maybe. Okay, so let's go ahead and proceed. So this is the first order condition, set it equal to 0. And we're going to solve for x2 here. So here I just rearrange stuff a little bit. Everything's still equal to, this is still just one way of writing the first order condition. I can then multiply both sides by y minus p2x2. I get this expression. After that, I get an expression that starts to have a little intuition associated with it, I think, which is that expenditures on p2x2 are multiplied by some constant, and so it's proportional to total income. And that gives me my final expression. And so I'm going to spend a little bit of time talking about this one. So this is a part of the solution here. This tells me how much x2 a consumer with these preferences will purchase given income y facing prices p1 and p2. Okay, so this is a nice sort of intuition to go with this. So first of all, I've got a number here, beta divided by alpha plus beta. Notice that by construction, if alphas and betas are positive, this is a number that has to lie between 0 and 1. Right, the largest beta can be, if beta gets really huge and we make alpha fixed, this number goes to 1 because of the alpha plus beta in the denominator. If beta goes down to 0, this is 0, of course. So this term here is a number between 0 and 1, inclusive. Okay, then we've got this other stuff over here, which is more interesting. Well, it's all interesting, really. Okay, so I've got income here. So how is, just looking at that, how is the consumer's choice of x2 going to depend on the size of the pot of money they've got? Well, so x2 and y. So as y gets bigger, what happens to x2? It gets bigger, and it gets bigger at a linear rate. The linear rate being this beta over alpha plus beta divided by p2. Okay, what if p2 increases? What happens to x2? Then it's going to get smaller. Is it going to get smaller at a linear rate? We've got p2 in the denominator. Does it never go to 0? What happens to x2 as p2 approaches 0 from above? It's going to go to infinity. The consumer always prefers more to less. So if the price of good 2 is 0, they demand an infinite quantity. If p2 is very small, they'll demand a lot, right? So no, it's not linear. The p2 is going to have an effect on this demand, which gives us back a hyperbola. Right? We saw hyperbolic indifference curves. This is related to that. As p2 goes to, this is, think of these as all being a fixed number, then we've got something like 1 over p2 here. So the effect of p2 on demand for the second good is going to be sort of hyperbolic. Okay, let's keep going. Yeah. Okay, so I got x2. We talked about some of the pieces of that. We can go ahead and use that now to solve for x1. The way I'm going to do that is by taking the solution I got for x2, that's just this thing here, and I'm plugging it back into the budget constraint, and still assuming that thing holds with equality. So it's just the budget constraint plugging in the optimal solution for x2. Okay, having done that, I got an equation that involves only a single unknown variable, x1, and so then I just solve this thing for x1, and a little bit of algebra gives me a solution that looks like this. And you can see x1 is equal again to a form, depending on this parameters, it's a number bounded between 0 and 1, times y divided by p1. Yes, Hillary? Okay, so Hillary's question is whether alpha and beta have some natural interpretation. And the answer is yes, they do, or maybe I should say that this ratio does. So you can see this. Am I going to say this? Let me put this on the board. I don't think this is redundant. So what I want to do is just, I have a very quick observation, which is I want to take this expression for x1. And what I'm going to do is rearrange it just a little bit by multiplying both sides by p1. And so what I wind up with is p1 x1 equal to alpha over alpha plus beta all times y. Okay, so written that way, what's the interpretation of the left-hand side of that thing? Expenditures on good 1. And y, of course, is equal to total expenditures. And so what's this alpha over alpha plus beta? It's the share. We'll call it the expenditure share for good 1. It's the proportion of your total income that this consumer will choose to spend on the first good. And this is a constant in this case. That's a feature of the particular utility function we've assumed. But that sort of feature shows up a lot. So the fact that this is a constant is special, but this kind of form shows up a lot in sort of empirical applications in economics. So we'll call this thing the expenditure share. And you can see it's related to these are preference parameters, we'll call them. These are numbers that enter the consumer's utility function that tell us basically how much the consumer wants to spend on good x1 versus good x2. So if let me give an example perhaps. If we have, x1 is equal to, coffee. We can do coffee and wine again. So if x1 is equal to coffee and x2 is equal to wine, then somebody really likes coffee will have a big alpha, and somebody really wants wine will have a big beta. And those two numbers together will pin down the proportion of their income that consumer will tend to spend on wine versus coffee. Okay, regardless of what prices are. If prices of coffee go up, this proportion still doesn't change. It doesn't depend on income either. If your income doubles, you'll still spend the same share on wine and coffee for these preferences. All right, is that clear? That's a good question, thank you. All right, so let me keep going. What I want to do now is go back and check this assumption. So remember, I solved this problem by first assuming that the budget constraint was going to be satisfied with equality. And now I want to go back and I've come up with a solution which uses that assumption. And now I just want to check and make sure that the solution I came up with doesn't actually violate any of the assumptions that I made to begin with. So I want to make sure that the solutions I came up with actually wind up looking like a solution to the unconstrained to the problem when the constraint is inequality. Okay, so that's straightforward here. I've got this thing that holds with equality. I just want to plug back in my solutions for x1 and x2 here, thus, and make sure that in fact this thing does hold with equality. And you can see this yields an identity, so that's all okay. So this is really just a check on the assumption and also on my algebra as I go on. Okay. All right. Your question? Go back. Yeah, go ahead. How far? Oh yeah, my clicker's not clicking. I'm going to go back one more. So your question is, I think, so you've noticed that P1 shows up in the solution for x1, but P2 doesn't. And conversely, P2 shows up in this equation, but P1 does not. Oh, well, it looks like it's missed. It looks like you have sharp eyes and I missed it. Thank you. Yeah, no, there should be, tell me your name again. Brianna, thank you. Oh, yeah, there should be, Brianna's absolutely right. This is a typo. There should be a P2 there. And if I checked carefully, I would have concluded that I made a mistake because this won't really yield the identity I was after. Thank you. Okay. All right, thank you, Rion. Okay, so what we've done here is really nice, and I hope you should pat yourselves on the back, because what we've done here is figured out a way to compute the Marshallian demand functions for the standard consumers problem, given these references at least. And so Marshallian demands here, I should be careful. Again, they don't depend. They can take this particular form we've got here, but in general, what we mean by a Marshallian demand function is a solution to the consumer's problem where the consumer's choice about how much X1 and X2 to consume depends on prices and depends on income. So what we've got here is an example of a case where we're able to solve for X1 and X2 just as functions of prices and income. That's the Marshallian demand function. Okay. So again, I'll say it again because it's sometimes confusing. This is an example of a Marshallian demand function because it depends, it's a solution for X1, depends on prices and depends on income. If we had a different utility function, we'd get a different solution that would still depend just on prices and income, but would have other stuff would be different. Okay, now here's a couple of graphs. We already talked about this a little bit, but let me return to this because it's quite important. So we talked about how when we solved X2, we could think about varying income, and we thought about how that would affect the total demand for X2, the solution for X2 we got. We also talked about what happened when we changed prices. So both those little thought experiments have pictures that go with them. They get special names because they're so central to economics. So the first of those is called the Engel curve. So the Engel curve is the answer to the question of how does the consumer's demand for a good change when their income changes. So we're going to, if we're drawing an Engel curve, we're thinking about an Engel curve, we're imagining that prices don't change, but that income varies. And so this is a nice tool for lots of things. You can use it to think about what happened for a given consumer if their income increased. So you might say, in this case, so you don't know what, it looks to me like I have a setup here for the Engel curve. So X1 is the thing here that's on the vertical axis, Y is on the horizontal. As income increases, total demand X2 is going to increase at a rate of beta over alpha plus beta divided by P2. You have a question? No, the demand function is, I can't draw it in a two-dimensional graph so easily. So this is the Marshallian demand function. It depends on prices and on income. What I'm doing here is I'm holding the prices fixed and just varying Y so that I can have a nice two-dimensional graph. That's all. Yeah. So this is an aspect of the Marshallian demand curve, maybe, if you like. Named after Ernst Engel, who we'll talk about more later. Okay, so anyway, so we vary Y. We can think about this as describing what a given consumer would do as their income increased. So if we think about the guy I talked about a moment ago who likes coffee, so he has a big alpha more than he likes wine, then the Marshallian demand, this would be the Marshallian demand, the Engel curve for wine in this case. He consumes more wine as his income increases, but the total share of wine is less than 1/2. So you can just see from the slope of this curve. You can also use this thing to compare different consumers if you think you know that their preferences are similar. So something that economists often do in practice is we'll think of a pretty broad category of consumption goods, so food and clothing perhaps, or even food and non-food. And we'll say, well, gee, I think that this population of people has similar preferences over food and other goods. And then what you can do is maybe it's hard to know what their wealth or their income is, but you can say, well, gee, it's relatively easy sometimes to measure how much food they're consuming as a share of their budget. So you can use the fact that some people are consuming this much food compared to somebody over here who's consuming this much food to draw an inference about what their underlying total welfare is, what their underlying income or wealth is. All right. Okay, questions about Engel's curve? Oh, one other thing I should say here. There's different people mean slightly different things when they talk about Engel curve, so this is just a warning. So I've drawn this curve so that the thing that's on the horizontal axis, the vertical axis is the quantity of the good that's being demanded. Sometimes this will be instead written in expenditure form. So the thing that would show up here will be prices times quantity, so expenditures on good one. And then sometimes it's actually written as a share of total expenditures. So sometimes you'll have the same Y on the horizontal axis, but the thing on the vertical axis would be P1 times X1 divided by Y. So you want to have just the share of expenditures there instead. All three of those we casually call Engel curves, but you need to be a little careful about what you're looking at or what you're drawing. Y, that's total income. Yeah. Okay, other questions? Yes. Yeah, okay. So thank you. That's a good question. So, Sarah? I'm sorry. V. Okay. You're Sarah. Okay, sorry. Okay, so V says, I thought we were holding Y fixed. Okay, that's right. So in the consumer's problem, it's more accurate to say the consumer is holding Y fixed. So the consumer takes their pot of stuff as given. They solve their problem. And now we, standing outside and observing this consumer, are asking the question, what would happen if they had a different quantity of Y than what they've got? So the consumer takes Y as given. We economists aren't concerned that way. Just the consumer. Okay, other questions? All right. Okay, there's another curve that goes with this. So let me go back, I guess. So this